Do you remember gradient descent? The algorithm that could get us the optimal value for the parameters theta. Well, there's actually another method to get this job done. But first, to recap, gradient descent iteratively updates the parameters so that every iteration we decrease the value of j. We keep on repeating this until we reach convergence, or in other words, until we end up close enough to the minimum of the cost function. And the values for theta that we now have at convergence are the optimized values that we will use to make our model. Now, what is this mysterious second method? Well, just as gradient descent, we can use it to optimize our parameters theta. However, instead of gradually getting better values for theta, this new method will calculate the optimal values for theta in just one step. So it's a way of analytically calculating the optimal parameter value. To get intuition in how this method works, let us look at an example where we just have one parameter theta1. Do you remember what it means if we have only one parameter? Well, it means we will train a model based on just one feature, for example, only using the amount of horsepower to estimate the price of a car. That said, the new method for finding the optimal parameters is called the normal equation method. And what it basically does, it calculates in just one step the optimal values. If you remember well, the optimal values for theta are found when we end up in the minimum of the cost function. And what indicates that we are at the minimum? Yes, you guessed right. It's the point where all partial derivatives of the cost function are zero. So the normal equation method lets us go immediately from our initial values to the optimal values, and these partial derivatives equal to zero is the key to it all. What the normal equation does, it sets all the partial derivatives equal to zero and then it solves for theta. It's actually just a bunch of matrix operations, and we are not going into detail of how it works. We'll just show you how you can use it in your machine learning applications. Mathematically, it can be proven that we can solve for the optimal parameters by calculating following term. We need to multiply the matrix that contains the input features with the same matrix that is transposed. Then we take the inverse of this new matrix and we then multiply it with the transpose of the input matrix again. And finally, we multiply it with y, which is the vector that contains the labels of the training data. Let us look to an example. From this dataset we get the following input matrix x and following output vector y. That's actually all we need to solve for theta. You can now implement this in the programming language of your choice. In Python, this might look like this. Alright, so here's the code we'll be breaking down. It's a Python script that calculates the optimal parameters, theta, for a linear regression model using the normal equation. Let's go through it step by step. Let's start with the normal underscore equation function. This is where the magic happens. The function takes in two parameters, x, which is our input matrix, already including the bias term, and y, which represents the labels. The function calculates the optimal parameters using the normal equation formula. Now, let's take a look at our example data. We have an input matrix x with 3 rows and 2 columns, representing one feature and the bias term for 3 training examples. We also have a label vector y with 3 labels to the 3 training examples. Finally, we print out the optimal parameters, theta, that we've just calculated using the normal equation. So we can now execute this code and we will get the optimal values for the parameters. That said, let us now look at some differences between the normal equation method and gradient descent so that we can find out when we should use which method. First of all, with gradient descent we need to find a good value for the learning rate alpha. With the normal equation method, we don't need to find a good value for alpha, so that's one thing less to think about. Next, with gradient descent we need to scale our feature when the ranges of different feature are far apart. With the normal equation we don't need to do that. That's another thing less to worry about. So far only benefits to the normal equation method. The downside of the normal equation method lays in the amount of features it can handle. If the amount of features n becomes very large, let's say over 1,000, then the normal equation becomes very slow. This is because the inversion of a matrix is very costly. It takes a lot of time to invert a matrix that is large. We know that this term gives us an n by n matrix. So inverting this matrix roughly has a cost of n to the third. On the other hand, gradient descent works well even when we have a lot of features. Gradient descent works even well if we have a million features. And finally, the normal equation doesn't work for more complex learning algorithms like logistic regression. So we can't forget about gradient descent. The gradient descent algorithm still stays very relevant in machine learning. So now that you have a new method to solve theta, I suggest you try it out, and if you have any questions, feel free to ask them in the comment section below.